Hi, my name is Andrew Dimmer, and in this video, we're going to be covering kind of a crash course into test-driven development. Now, what is test-driven development? Test-driven development is a way of writing software such that you can increase the testability and the reliability of the software by writing your tests the same time that you're writing your actual production code. Now, test-driven development in and of itself is a huge topic, and it provides a ton of different benefits, including increased code reliability, increased code coverage, the ability for your code to be kind of more self-documenting. It makes your code more efficient, and it also means that when you come back to your code, 2 months from now, and you go, "What did I do?" It'll help you figure that out for you based off of the test cases you have, and you can be confident that you won't accidentally break your code. Now, test-driven development, again, big topic. If you want to learn more about the theory, you can Google it. But in this video, what we're going to be doing is basically walking you through, if you're told you need to use test-driven development, kind of what steps do you take to do it? So the first thing that we're going to talk about is how to determine a test plan for test-driven development. So the big thing for test-driven development is you write your tests before you actually write the code that you're going to test. Now, why is this? Because if you can't justify a use case where you need to test that it works correctly, why are you writing the code? It's one of those things where if nobody's ever going to use it, why would you program it? So what our goal is to, before we start writing any code, is we're going to develop a test plan. Now, what is our test plan based on? The test plan is based on the user requirements that you're given. So for this particular example, I'm going to be building a location data point class that stores the latitude and longitude at a specific point in time, and that is basically the purpose of my class. Now, I've been given a UML diagram down here of what I think this class should look like, according to basically my client. And you'll notice here that we have these three methods in green in particular, the getLat, getLong, and getTime method. Those are the equivalent of the public interface. So if you actually have a class that implements public interfaces, then obviously you go to the public interface directly. If you're implementing just a regular class, the first thing you've got to kind of do is figure out which functionality you expose to the user. Now, the reason that you want to do this one first is because, again, this will kind of help guide you what use cases you're going to come up with. So if you know through, and generally this is told to you by the consumer, you'll know, hey, you need to provide the latitude, you need to provide the longitude, you need to provide the timestamp. And, that's what we're looking to do. So we have that. And that's a good start for our test cases. We know that we'll need at least one test case for every public method that we're given. But it's important to note that just being given, here's the interface, build some test cases for it, that's not enough. You need to know what goes on behind the scenes. Now, something that's really interesting about software testing is you only ever test public methods. So if it's not visible outside of the class, you don't write a test case for it. Here's the thing though, any internal implementation you have in the class still gets tested because you don't have internal implementation in a class that's not ever called by somewhere outside the class. So I wouldn't write a method in a class that nobody ever can call, So even though we're not writing test classes for our private methods, we still test them throughout the process. But how we write our private methods is kind of generated during the course of test-driven development. So again, we have our public methods. We know we're going to need at least one test case there. However, we'll probably need more than one test case. The reason being is that some of these methods may have more than one user requirement tied to them. So, for example, for this location data point class, I know that I need to be able to go plot any location data point that I have on a graph, which makes sense. Basically, I need to make sure that my latitude and longitude are valid on a graph. So, longitude needs to be between negative 180 and 180. Latitude needs to be negative 90 and 90. Here's the thing, though. I also know that the system that's going to generate these location data points doesn't keep track of what's valid and what's not for latitude and longitude. So that's one of the requirements I have. The system that's generating these will basically tell me, go west 210 degrees, and I need to go through and calculate, well, that's actually 150 degrees east. So those are the requirements. Now, how do we start generating test classes for this? So the first thing you're going to want to do is you're going to want to go through and basically say a requirement and come up with what needs to be tested for it. So the first thing that we have here, my requirement is I need to be able to get the longitude. Okay? Well, if I need to be able to get the longitude, I also need to be able to set the longitude on construction. So a simple test case here would be that the longitude in is the longitude out. And because we'll be using JUnit to go test this, everything will be a void return with no arguments there. So that's my first test case. And that's going to be testing the float getLong method and kind of the constructor as we go through. Now notice, just because we've covered this doesn't mean we're done with that getLong method, because now I go through and I think, well, hey, I've got a use case where if I tell the system to go walk west, 210 degrees, we cross the anti-meridian. We need to be able to handle that rollover. So another test case I might have is that we cross anti-meridian west to east. So I need to make sure that that gets handled there. Now, on the other side, I can go through and I can cross that from east to west. So that's another test case. And then finally, I'm going to go through and do one more test case. Let's say that I happen to go around the globe multiple times, and I cross all of these multiple times. What happens if I want to go through that more than once? So those are kind of the test classes that come up for the longitude, based on the information that I know. The other thing I want to go highlight is that in terms of test cases, you should have a couple different types of test cases. So your first one is your expected test cases. So that's kind of the first three. We know we're going to have a latitude in, we know we're going to need it out, and that can handle all of our valid latitudes. Then these two, the anti-meridian west to east and east to west, goes through and basically say if I have a number that's too small or a number that's too large. And then finally, those are traditional cases. The other thing we've got here is we have the extreme cases or the edge cases. So an extreme case is you go around the globe multiple times. That's going to be something we need to test. Now, some other edge cases we need to go handle for this time, though, is we need to make sure that not only is time in is time out, but we also need to make sure that null time not allowed. So while we're handling the test case that says you're not allowed to have a null time, some other common edge cases you might want to go test are empty arrays or empty strings, null pointers. If you have negative numbers and you're not allowed to handle it, if you've got a maximum for some of your numbers for that sort of thing, any of that are all edge cases to go and think about. So that's kind of the process of the design. Now, one more thing I want to note in terms of design, if you're given something like a UML activity diagram, then you're not quite going from all the requirements as kind of like an abstract sense like I did here, but you kind of know some of that internal implementation. And the general thing for code coverage is you need to have at least one test case for every branch of the code. So if you have an if statement inside of a method, you're going to need at least 2 test cases for that method. You're going to have, test case when if is true and test case when if is false. So just in terms of generating test cases, those are some common things to go keep in mind. Now, once we've gone through and we've generated our test cases, the next thing we need to do is we're going to stub out some of the implementation. This can also be called mockout sometimes, depending on what software you're using. So what is a stub? Well, a stub looks something like this. Now, this is the location data point class stub. And as you can see, if we're looking at it from the public methods, based on the interface, the longitude, the latitude, and the getTime, all of those are fully implemented. So for any class that's looking in on our location data point, it contains everything that it expects to get. Now notice here, this doesn't actually do anything. This is only the bare minimum code to go expose the methods to other classes and basically make sure that it compiles and doesn't throw you compiler errors. Now, why do we do this first? Well, putting it simply, you know that you're going to have this basically from your user requirements. If you can't get which information you need to expose to other classes that consume your class, then you need to go prompt for more requirements, generally speaking. So we'll know what this public interface is. And we need this because we're going to actually need to create a copy of the object in our test cases. So there's no point writing a test case for an object that physically doesn't exist, because then your test case is going to fail saying it won't compile. You're not testing anything. You're just saying that, yeah, it's not valid code. It won't compile. Now, the other thing I want to point out here, this stub is when we're going to build. If you have a dependency on other classes, so notice here we have a local date time class. Traditionally, anytime you have dependencies on other classes, you also mock out those classes, or you stub out those classes. Now, why do you do that? Well, the biggest reason here is that if you're writing a unit test, you want to make sure that if your test fails, it's because of something that you wrote and not something that you're consuming as basically as another class. So if someone downstream wrote some new code and they broke your tests, you want to be, isolated from that. You don't want that to happen. So what you do is you go through and you stub out any and all classes that you consume. That way, you know that any tests that fail are strictly because you've changed code, not someone else has changed code. At least at a unit test level. Obviously, integration tests, that's a little bit different. But for unit testing, you want to go stub all that out. Now, you can do this with a software like Mockito, or you can write the stubs yourself. Either one is okay, but that's important to do. The other thing is that you generally don't want to have constructors for other classes inside of your class. It makes it much harder to test because you can't stub those out, and you're entirely reliant upon their implementation to be able to go run those tests. So a common software architecture you can use for this is called dependency injection. So as you can see, I need a local date time, but instead of creating a local date time inside of my class, I'll take that in through the constructor and save it. And in doing so, I can go through and replace that local date time, that actually is a production class, with a stub if I needed to. Now note here that local date time is actually a Java class. So I'm relatively confident that Java is going to work the way that I think it will. I don't need to go stub that one out in this case. But it's worth noting that you do generally stub out any other dependencies that you have if you're not sure that they're going to work. Now, finally, what we're going to do is we're going to actually start building our test cases and writing our code and iterating and things like that. So the first thing we do, we're going to head over to our JUnit test class here, and we're going to write out the first test case. So the name of this test case, we're going to prove that longitude in is the same longitude out. And the method name, we'll give it the same thing. Long in is long out. And inside of our test implementation, what are we looking to do? Well, we go through and we create a new location data point. So location data point, LDP is equal to new location data point. And at this point, note that we only have the basic constructor there. So we'll give that. And then we're going to basically, we'll need to go set our latitude. Always helpful. So we have our float, our longitude is, and here's the thing, for test cases, generally speaking, you want to go through and use random inputs. Now, the reason for this is it makes it much more complete, I guess, so that you don't end up with a hard-coded example, because if you hard-code something, you only know that that hard-coded part is working. If you go through and you've got random examples and you run this multiple times, you'll be pretty confident that it's actually working. So we're going to do math.random times 360 degrees minus 180. Okay. So that'll generate our random latitude. And then finally, for our test case, we need to assert that the expected longitude is what we get from our method there. So that is our test class right then and there for verifying that the latitude that we put in is the same, or the longitude we put in is the same longitude we get out. So if that's the case, we can save it. And I'm actually going to run the tests. And I'm using Gradle as a build framework for this one, so when I build it, it will also test. So we've written our test case, and notice that it failed. Why is this? Oh, it's actually a compiler error. Oh, I forgot to import location data point. That is important to go through and do. Import edu. Okay, that should do it now. If we go through and we save it, build it, okay, so notice that the build failed. And if we actually scroll up, the reason it failed is because testing failed. Well, what failed was that the longitude in is not the same longitude out. The assertion failed. Hey, darn, I'm shocked. Our test case failed. It's almost like we don't have any production code here. Well, okay, that's fine. Now we just need to go through, once we have a failing test, that dictates, yeah, we don't have all the implementation we need. It's time to go actually write code. So, to do this, now after we have our failing test, we're actually going to write our production code. So, what do we know we need? We know we need a way to set it, and in this case, we're going to set it through the constructor. So we have location data point is going to take in a float longitude. And what else do we know we need? We know we need to set it. So we have a final float longitude. And we believe that this dot longitude is equal to our input. And finally, we're going to return longitude. So notice for this one, we have a failing test case. Then we write the production code. Now, if we test it again, the build is still failing. Oh, okay. Here's an important one. We've changed the constructor. So we need to go modify our test case a little bit for this one. We now pass in the longitude there. Once we save that, we test it again. The build is failing. What else is going wrong? Oh, we need to go through and make that a public constructor. Okay. Now we can go through, we build it again. And you'll notice the build is successful because our test passed. Now, after the test passes, now we can go through and we do what's called refactor. And so in doing so, we basically clean up this code. Now, is there any code to really clean up here? Not really. So if that's the case, we've got one test case passing. We're ready to move on to the next test case. So we head back over here. We don't write any production code. We head right back to our test cases, and we're going to build another test case. So for this one, we're going to say that the name is longitude rolls over when crossing the anti-meridian from, our first one is west to east. And again, we're going to go give it the name. So that is cross anti-meridian. I think I misspelled meridian. Well, the great thing about code is we can go through and change it. So we're going to grab U, meridian, update that. There's the new render. Crossover anti-meridian. And then we have cross anti-meridian. This one is west to east. And so what do? We generate another location data point here. But what do I know about this location data point? Well, I know that we've got to cross the anti-meridian. So what we're looking for is something that is from west to east in particular. So if I'm going west to east, it means that my location data point is below 180. So what I'm going to actually do here is to randomly generate it. I'm going to say we're going to generate a valid point, and then we're going to subtract 360 from it. Now, there's one other edge case about this random generation, is that both 180 and negative 180 are valid. So if I randomly get 180, I don't want to pass this test case when negative 180 is a value. So what I'm going to do here is just to make sure that I don't ever get positive 180 as a test case, I'm going to change that to 350. We're going to do 175. So now effectively it's between negative 175 and 175. We cross the anti-meridian for it, and now we're good. So what we're looking to do here is that the longitude should be equal to the get longitude. And I'm actually going to change that here. So what we do is we generate basically our correct answer first. We modify the correct answer to say, we've actually crossed the anti-meridian. We went around the globe one time, and in doing so, we crossed the anti-meridian exactly once. And so the longitude we get out should be the same longitude that we, generated to begin with. So now we have a test case again. We save it. We test it. And when we look at it, hey, our build is failing again. Well, why is our build failing? We've got another failed test case here. Now notice, we can still see we're passing the previous one. So we know that's working. But we also know this one is specifically failing. So now that we have a failing test case again, we will go back to writing production code. Now, what we could do here is, because this is just enough to get it done, we're going to say that if longitude is less than negative 180, then we're going to go through and we do longitude plus 360, because we know that 360 degrees around the globe, that'll be the same longitude from basic circle geometry. Otherwise, it's longitude. So this is a test case that I think is going to pass. We save it, we build it, and the build is still failing. And notice really quickly here, we didn't break our existing test case. So we know that that's still working. We just need to go figure out what's going on with this. And I think this could be a quick arithmetic one. Let me try 0.01 there, see if that does it. Yeah, okay. So really quickly, the reason we were failing that last test case was because when we did the math for it, the math to go subtract and the math to go add wasn't exactly identical based on how the computer stores the numbers in binary, because it doesn't store, floats to the exact precision. So I just set a precision of 0.01. And in fact, I'm probably going to do 0.001 for this one, just because that's the accuracy of the float that I care about from a GPS perspective. So if we build that, I'm going to add that to our test case up above there as well. There we go. Okay, so now we have another passing test case. Now it's time to go through and take a look at this code. Could we make this more efficient? Well, I don't really like that we're calculating it on output. I think that this should be its own method. So what we're going to do is I'm going to go through and we'll create a private method. Now remember, we don't go through and test private methods, but that's okay because it'll still get tested when we go through and basically generate our public test classes from when we call it. So we're going to say that this is normalize longitude. We'll take a float longitude in, and then we'll return that method there. Now, the reason we're doing this is because I'm going to go normalize it before we store it, because I know from my use case that I may run the get multiple times, but I'm only going to store it once. So while the previous one passed the test case, and it was arguably the simpler solution, I know that this one is going to be a little bit more efficient, both in terms of code cleanliness and in terms of the, efficiency of running it. Now, once I've made my changes again, even before I add any new test classes, it's really important you verify that your new changes, when you refactored it, don't break the code. So you notice we currently have the build failing again. Oh, I'm guessing that's a missing semicolon from a compiler. Yeah, that's missing semicolon. Okay. Why we test it? Now if we go through, we test it, we go take another look. Did I not spell it right? Nope, that's a spelling error. Okay. Copy, paste, save, test. And notice that all of that is verifying that each time we do it, we haven't changed the functionality. So again, we've got another passing test case and we're good. Now we would go through and we would keep doing this for each of our different test cases until we have a final class written where all of our test cases are passed. And, make sure that you generate all the test cases too, because we haven't touched latitude here. You need to go generate those test cases as well. That said, that's a brief introduction to test-driven development. I hope that helps, and if you want any more help with this, just feel free to Google it. There are tons of great resources all over.